2026 RISC-V Linux ecosystem, how mature is it today? Chapter 1 Introduction. In the previous video, we explained why Linux and RISC-V are such a natural match. RISC-V provides an open instruction set architecture. Linux provides a mature open-source operating system ecosystem. But a good match in theory does not automatically create a mature platform. So today, we will ask a practical question. What is the real state of the RISC-V Linux ecosystem in 2026? Can you install a modern Linux distribution? Can developers compile and test real applications? Can RISC-V support desktops, cloud workloads, virtualization, artificial intelligence, and servers? And what is still missing? By 2026, RISC-V Linux has moved far beyond the experimental stage. It now has mainline kernel support, official distribution support, modern toolchains, standardized processor profiles, real hardware, and growing cloud-native infrastructure. However, it is not yet as complete, consistent, or consumer-ready as x86 or ARM. The ecosystem is real. The foundation is strong. But the final layer of standardization, performance, drivers, and polish is still being built. Chapter 2. The question has changed. A few years ago, the main question was, can Linux boot on a RISC-V processor? In 2026, that question is outdated. Linux can boot on many RISC-V systems. Developers can run shells, compilers, package managers, web servers, containers, desktop environments, and many other applications. The new questions are harder. Can one distribution support different boards without a custom image for each one? Can a system use a recent mainline kernel instead of an old vendor kernel? Are graphics, storage, networking, power management, and peripheral drivers available upstream? Can virtual machines run reliably? Can software projects test every code change on native RISC-V hardware? These questions show that the ecosystem has entered a new phase. RISC-V Linux is no longer only proving that it works. It is trying to become standardized, maintainable, scalable, and production-ready. Chapter 3. Mainline Linux is the real foundation. The Linux kernel has supported RISC-V for years, but that support now goes far beyond simply booting the processor. Upstream Linux includes RISC-V support for the user space application binary interface, virtual memory, hardware feature detection, vector instructions, security mechanisms, and ACPI-based systems. A modern operating system also needs timers, interrupts, multi-core startup, PCI Express, storage, networking, debugging, performance monitoring, virtualization, and security. More of these capabilities are entering the mainline kernel for RISC-V processors and system-on-chip platforms. This upstream model is essential. When a driver is merged into mainline Linux, every distribution can use it. The wider community reviews it. Future kernel releases are less likely to break it. Security fixes are easier to deliver. And users become less dependent on one hardware vendor. Without upstream support, a board may run Linux only through a customized manufacturer kernel. That kernel may be old, filled with private patches, and difficult to upgrade. So the best measure of progress is no longer the number of boards that can boot Linux. The better measure is how much hardware support has reached the upstream kernel. Chapter 4. Linux distributions have reached a milestone. One of the biggest signs of maturity is official distribution support. Debian 13 became the first stable Debian release to officially support the 64-bit RISC-V architecture. This is a major milestone because Debian is both a widely used operating system and the foundation of many other distributions. Official architecture status means RISC-V packages are built, tested, maintained, and released through normal Debian infrastructure. Ubuntu has also made a major commitment. Ubuntu 26.04 LTS supports the modern RVA23 profile for RISC-V application processors. Long-term support matters to companies because it provides a stable software base for many years. However, at the time of the Ubuntu 26.04 release, QEMU remained the primary supported RVA23 platform because compatible physical hardware was not yet widely available. But there is an important transition. Many older boards implement earlier profiles, while newer Ubuntu releases require RVA23. Older systems can remain on Ubuntu 24.04 LTS, while new hardware is expected to move to the modern baseline. Fedora has an active RISC-V port, but it is still not an officially supported primary architecture. Fedora's own documentation describes the current experience mainly as a headless build host or server environment, and notes that integrated graphics support is often missing from mainline Linux. Other communities, including OpenSUSE and several RISC-V focused distributions, are also building packages and images. The distribution ecosystem is much stronger, but support levels are still uneven. Chapter 5, RVA23 reduces fragmentation. RISC-V is modular. Designers can select extensions for different markets. That flexibility is powerful, but it can also fragment software. If every processor implements a different combination of extensions, developers cannot rely on a common feature set. RISC-V profiles address this problem. A profile defines capabilities that software can expect from a class of processors. In 2026, RVA23 is becoming the key baseline for modern 64-bit application processors. It gives operating systems, compilers, libraries, and applications a more predictable target, including modern vector processing capabilities. This does not eliminate customization. Vendors can still add optional extensions and accelerators. But profiles create an essential balance. Hardware companies keep room to innovate, while software developers gain a stable target for compatibility and optimization. Ubuntu's move to RVA23 shows that profiles are now shaping real operating system policy. Chapter 6, Server Standardization took a major step in May 2026. Version 1.0 of the RISC-V server platform specification was ratified. This is one of the year's most important ecosystem developments. A server needs much more than a fast processor. The operating system and hypervisor must know how the machine boots, how processors and devices are discovered, how interrupts work, how PCI Express is connected, and how firmware and security services behave. The server specification defines capabilities that portable operating systems and hypervisors can rely on. It requires modern RISC-V application processor features and builds around standards such as the Supervisor Binary Interface, UEFI, and ACPI. This matters because data centers cannot accept a different custom boot process for every server. Linux distributions need standard installation methods. Hypervisors need stable interfaces. Hardware vendors need a clear target. The specification does not instantly create a mature RISC-V server market. Compliant hardware, firmware, testing, management tools, and enterprise support still have to follow. But it creates the rules of the road. Chapter 7, the boot stack is becoming more standard. A RISC-V Linux system normally contains several boot layers. Platform firmware initializes the hardware. OpenSBI commonly provides the standard supervisor binary interface between machine mode firmware and the operating system or hypervisor. Then U-boot or a UEFI implementation loads the Linux kernel and its hardware description. Many development boards still rely on device tree and board-specific boot flows. That works well for embedded systems. Servers and general-purpose computers increasingly benefit from UEFI and ACPI, which make operating systems more portable across machines. Both models still exist in 2026. That is normal during an architectural transition. The goal is not to force every device to boot in exactly the same way. The goal is to reduce unnecessary vendor-specific behavior. Chapter 8, Real hardware exists, but it is still developer-focused. The hardware ecosystem now includes low-cost single-board computers, compute modules, many-core development systems, FPGA platforms, and laptop mainboards. A RISC-V mainboard has even been sold for the framework Laptop 13. That is significant because it puts RISC-V into a familiar laptop form factor. But Framework described it as a developer-focused product, not a consumer-ready experience. That warning reflects the wider ecosystem. You can run Linux, compile software, develop drivers, test applications, use containers, and experiment with desktop environments. But you should not expect every board to behave like a mature x86 or ARM computer. Graphics acceleration may be incomplete. Video decoding may depend on vendor software. Suspend and resume may be unreliable. Wi-Fi, Bluetooth, audio, cameras, and power management may require board-specific fixes. Some systems still ship with old kernels because complete hardware support has not reached mainline Linux. The hardware is good enough to build the ecosystem. It is not yet consistent enough to disappear into the background. Chapter 9, Native testing is changing the software ecosystem. One of the most important changes in 2026 is the growth of native RISC-V continuous integration. For years, many projects supported RISC-V mainly through cross-compilation or emulation. Those methods are useful, but they cannot replace testing on real hardware. The RISE project now provides managed RISC-V runners for GitHub Actions. During its early availability period, the service processed more than 13,000 jobs from nearly 200 repositories. Projects involving artificial intelligence inference, scientific Python, cryptography, databases, containers, and cloud-native infrastructure are beginning to test directly on RISC-V machines. Llama.cpp has tested changes on native RISC-V hardware. Work is also expanding toward PyTorch, NumPy, Kubernetes-related projects, containered, and lightweight Kubernetes distributions. This is how an architecture becomes a normal software target. A developer changes the code. Automated systems build and tested on x86, ARM, and RISC-V. Architecture-specific failures are found before release. Over time, RISC-V stops being a special port tested occasionally. It becomes part of everyday development. Chapter 10 Toolchains are strong, but platform quality is uneven. The core development toolchain is now one of the strongest parts of the ecosystem. GCC, LLVM, binoodles, debuggers, C and C++ libraries, QEMU, and many language runtimes support RISC-V. Developers can cross-compile from another architecture, build directly on native hardware, or run a complete virtual machine through QEMU. Optimization is not finished. x86 and ARM have benefited from decades of compiler tuning. RISC-V still needs more work in vector code, cryptography, artificial intelligence, and processor-specific optimization. But basic software development is no longer the main barrier. The larger challenge is platform quality. A compiler may generate correct code, but the machine still needs good firmware, a recent kernel, complete drivers, reliable graphics, and proper power management. Chapter 11 Virtualization and cloud support are promising but uneven. RISC-V supports virtualization, and Linux can use QVM on suitable hardware. QEMU is already a valuable environment for developing and testing RISC-V virtual machines. The new server standards also provide a clearer foundation for future cloud platforms. However, virtualization remains uneven across available systems. Some processors lack the required extensions. Some vendor kernels do not contain recent QVM support. Some platforms still have incomplete interrupt controller, IOMMU, or firmware support. RISE has noted that some current native runner machines use an older vendor kernel and do not support virtualization. That example shows both progress and limitation. Native RISC-V cloud infrastructure exists and real projects are using it, but parts of the stack still depend on older platform software. More RVA23 hardware and more mainline SoC support should make virtualization increasingly routine. Chapter 12 The biggest remaining problem is outside the ISA. People often discuss fragmentation in RISC-V instruction extensions. Profiles are reducing that problem. But the more serious fragmentation often exists outside the instruction set. Boards use different boot flows. Vendors ship different kernel trees. Peripheral controllers vary. GPU drivers vary. Firmware and documentation quality vary. Some vendors upstream support early. Others release a private software development kit and stop there. RISC-V is an open instruction set, but a complete computer may still contain proprietary firmware, closed drivers, and undocumented accelerators. That is why upstream development matters so much. A slightly slower board with excellent mainline support may be more valuable than a faster board trapped on an obsolete vendor kernel. Chapter 13 How mature is RISC-V Linux in 2026? The best description is this: RISC-V Linux is now a credible development and early deployment ecosystem, but not yet a fully mature mass-market computing ecosystem. For embedded Linux, education, research, custom processors, edge computing, and software porting, it is already highly useful. For developers who want to help build the platform, 2026 is an exciting time. For ordinary desktop users expecting perfect graphics, multimedia, sleep support, and plug-and-play peripherals, the experience remains inconsistent. For servers, the standards are arriving and the software is advancing, but large-scale enterprise deployment is still early. For cloud-native software and artificial intelligence, native testing and vector-capable hardware are creating real momentum. RISC-V is not replacing x86 or ARM overnight. The more important story is that it has crossed a boundary. It is no longer only an interesting instruction set. It is becoming a complete computing platform. Chapter 14 Conclusion The RISC-V Linux ecosystem in 2026 is defined by 5 major changes. Mainline Linux and the core toolchains provide a serious technical foundation. Debian and Ubuntu have moved RISC-V closer to normal distribution support. RVA23 is creating a modern baseline for application processors. The ratified server platform specification provides a common direction for servers, firmware, and virtualization. And native continuous integration is bringing RISC-V into the daily workflow of major open-source projects. The remaining challenges are equally clear. More hardware support must reach the mainline kernel. Graphics and multimedia drivers must improve. Old vendor kernels must be replaced by upstream support. Virtualization must become consistent. And more affordable RVA23 hardware must reach developers. An ecosystem is not created by a processor alone. It is created by standards, firmware, kernels, drivers, compilers, distributions, applications, testing infrastructure, hardware vendors, and open source communities working together. RISC-V opened the processor architecture. Linux opened the operating system platform. In 2026, these two open ecosystems are no longer simply a perfect match in theory. They are building a real computing platform together.